Welcome to ES 310 Lesson 26. Today we will be starting the work energy section of the class as applied to rigid bodies. We will start by reviewing work energy applied to particles and then talk about the differences that occur when we have a rigid body. We'll look at both kinetic energy and the work, and then we will do several examples where we apply the principle of work energy to rigid bodies. More information about these topics can be found in Hibbler's Dynamics textbook, Chapter 18, Sections 1 through 4. So think back to work energy methods for particles, and we had an expression for the kinetic energy, which is 1/2 of mass times the velocity squared. So this is always a positive quantity, and it's measured in joules. We also had expressions for work. The general expression for work is the integral of the force dotted with the distance. So you're looking at the force times the part of the distance that is parallel to the force. The work that gravity does is with respect to the weight, and we're always looking at a vertical distance because weight is always vertical. Gravity does negative work if we move upwards, and positive work if we move downwards. A spring has a work expression of 1/2 K S2, which is the final stretch in the spring, squared, minus S1, which is the initial stretch in the spring, squared. The principle of work energy says that the initial kinetic energy plus the work done on the system is equal to the final kinetic energy. So that was for particles. Now we'll take a look at how these change for rigid bodies. So rigid bodies can also translate. The expression there is much like that of a particle, but we're limited to talking about the speed of the center of mass. So G is the center of mass. If we have a fixed axis, we can write the total kinetic energy as two terms with respect to the center of mass, or as a single term with respect to the fixed point. So the top equation here is for center of mass, and this equation is for fixed point. So for the center of mass, we have a translation part of the kinetic energy because the center of mass is translating, even though point O is fixed. And we have a rotation part of the kinetic energy, which is 1/2 Ig omega squared, since there's energy because it's spinning. If we translate this Ig into Io by using the parallel axis theorem, we can write this as a single term because point O does not translate. So the translation part of the kinetic energy for point O is 0, and the rotational part of the kinetic energy is 1/2 Io omega squared. So in general plane motion, then, where things are not fixed at a point at all, we have that kinetic energy is the translational part for the center of mass plus the rotational part around the center of mass. If there happens to be an instantaneous center of zero velocity, this reduces to a single point because we can treat that instantaneous center of zero velocity as a fixed point, like in the equations above. So the second part of the work energy method is to find the work. Most forces on rigid bodies will do work exactly the same as they did before. If the force and the distance are in the same direction, they're positive. If the force and the distance are in opposite directions, they're negative. You need to know what point you're looking at, but that's the point where the force is applied. So you look at if the force is applied to a point on the rotation, then you look at the distance that point moves, and those are the two quantities you're looking at. Notice some forces don't do any work, and this was true for particles as well. So forces that act at fixed points don't do work because the distance is 0, the point isn't moving. Forces that act perpendicular to distances or displacements don't do work. So in this case, if this ball or this cylinder is rotating and rolling, W is not going to do any work because it's acting perpendicular to the displacement because it would be moving in that direction. N, likewise, is not going to do any work. The friction is not going to be do any work because this is the instantaneous center of zero velocity. So this point is a fixed point instantaneously. So F, the friction, has no distance through which it works. Something that's new for rigid bodies is that in rigid bodies we could have applied moments or couple moments. The work done by a couple moment is the integral over the angular displacement of the moment times the change in angular displacement, d theta. So if it's a constant moment, we can get rid of the integral and we have the work is equal to the constant moment times the initial position minus the final position, which is much like work in the linear domain where it's force times the initial position minus the final position. So the principle of work energy hasn't changed. We still have the initial kinetic energy plus all of the work is equal to the final kinetic energy. Our procedure is much the same as well, except we've added the need to look at rotation. So to find the kinetic energy, you look at your situation and you find the kinetic energy of the various parts of your system. You might need to use kinematics in order to find the angular and linear velocities, and you will need to use kinematics to relate them as well. So relate V's and omegas. Usually it's easiest to relate everything to omega, and we'll see that in the examples. So draw a free body diagram, identify all your forces and couple moments that do work, and notice that many of them might be on there but not do any work. And then find your work. Pay attention to your signs. Right? So positive if the force and the distance are in the same direction, negative if they're in opposite directions, and then apply the work energy equation. So let's take a look at an example of this. We've got a double pulley. So we've got this rope that comes up, wraps itself around the pulley, and comes out on a smaller pulley on the other end. They're fixed together, so any motion of one part of the pulley is the same as the angular motion of any other of the other part of the pulley. And you've got 20 pounds attached to the outside pulley, 30 pounds attached to the inside pulley. Both of those are weights, so let's draw the weight arrows. And you've got a fixed point in the center that's holding everything up. The pulley is initially rotating at 20 radians per second. This is a negative, right, based on the direction it's drawn. And we're given some information and asked to figure out, once this weight has moved down here 2 feet, what is omega? So let's start by writing the expression for the kinetic energy. The general expression for kinetic energy here, we have 3 objects that are moving. We've got block A and B, and then we've got the pulley. So the kinetic energy for the pulley is 1/2 I/O omega squared, right? And so that's it, because O is both the center of mass and the fixed point. So we're treating it as a fixed point. The pulley itself doesn't translate, so that is the kinetic energy for the pulley. Then we have the kinetic energy for each of these blocks. So we have 1/2 of the mass A times VA squared plus 1/2 mass B times VB squared. Okay, right now we have one equation and 3 unknowns. And so we need to try to relate these unknowns. The unknowns are omega, VA, and VB. So can we relate omega to VA and to VB? So if we look at the pulley, the relationship is going to come about through the radiuses. So you can probably figure this out just by looking at it, but if we think back to our velocity equations, our relative velocity equations, we have VA is equal to VO, which is our fixed point, right, plus omega crossed with R. So VA is equal to omega is negative K hat, R is positive, let's see, these are our R's right here and here. So this is RA, negative omega crossed with positive R J I hat. Negative gives us a negative VA. Right, so that would be a negative omega RA. We don't know omega, but we do know RA, so this is going to be negative RA is 1 times omega. You do the same thing for VB. Omega crossed with RB. RB is in the negative J hat, so negative K hat crossed with negative J hat gives us positive R, positive J hat. So we have positive omega RB, which is 0.5 omega. Now technically for the kinetic energy, those signs don't matter because we're going to square both of the velocities. But we can now plug these in, and there's going to be an omega squared in every term. So we have T is equal to 1/2, pause for a second and find IO. IO is equal to the mass times KO squared. KO is given to us. So this is 50 over 32.2 times 0.6 squared. So that goes in here, 50, 32.2 times 0.6 squared, that's IO, and we have omega squared, which is our unknown. Plus 1/2 mass of A is 20 pounds divided by 32.2, times VA, which is RA omega, so that's 1 squared omega squared. And the negative gets squared and becomes a positive. Plus 1/2 of 30 divided by 32.2, so for block B, times 0.5 squared omega squared. So now our only unknown here is omega squared. We can actually crunch all those numbers and we get 0.7065 omega squared. So now we need to do the work. So if we're looking at this system, the only two forces that are doing work on this are WB and WA, right? The force in the cables are internal, so that doesn't do work. There are no forces acting on this pulley except the ones on the pins, and that pin isn't moving, so that those forces aren't going to do any work. So the only two forces we're worried about are VA and VB. VA, since this is moving downwards, is going to do positive work, and WB is going to do negative work. So our work then, 1 to 2, is going to equal WA doing positive work. So WA times the distance WA moves, or the block A moves, minus WB doing negative work times the distance that block B moves. So now we need to figure out what LA and LB is. So this 2 feet is LA, right? The distance that the 20-pound weight A moves is 2 feet. How do we relate LA to LB? So let's look at the pulley. If this moves LB, then this point here, the rope, is going to move LB. The distance that the pulley will turn as that happens is going, let's call that theta. So theta is going to equal LA divided by the radius 1. Right? So that's rewriting the distance a point on a circle moves is theta times the radius. Well, both of those pulleys are going to move the same theta because they're physically rigidly attached to each other. So this is also then going to equal LB times the radius to B, which is 0.5. So then we have, and one is positive, one is negative, but the signs are already incorporated in our work expressions over here. So we get that if LA is 2, LB is 0.5 times 2 divided by 1, which is 1. So then we can plug that in over here. WA is 20 times 2 minus 30 times 1 gives us 10. And we can apply our work energy. So T1 is plus U from 1 to 2 is equal to T2. T1 is 0.7065 from before times omega 1 squared. Omega 1 squared plus 10 equals 0.7065 omega 2 squared. Omega 1 is equal to 20. And we can solve for omega 2, which is 20.35 radians per second. So, in review, 3 steps: kinetic energy, work, and work energy. And on the side, we have some kinematics that are relating our variables together. So, one more example. We have here, we have something that is rolling. So it is not fixed at its center. So I'm going to, just to avoid confusion, change this point O to point G, the center of mass, because typically we use point O as a stationary point. But in this case, point O is not a stationary point. So we're going to change the letter just to avoid confusion here. So we have a 50 kilogram gear, got its radius of gyration, so we can find its moment of inertia, and it says it is around its center of mass, so that's Ig is equal to mass 50 times radius of gyration squared. So we have our IO, or Ig, sorry. Alright, then we can look at the rest of this. If the gear track B is stationary. If the gear track B is stationary, this point, the contact point at the bottom, is our IC, right? Because VB is 0. Sorry. VB is always 0. The gear is meshed with that track, so that point is not moving. Okay, so that's our IC. Then we have a 25 kilogram rack up here at the top, which is the C rack, and it is moving because it's being pulled by a force of 150 newtons. We want to figure out the speed of this rack up here after the center of the gear has moved 3.3 meters. So, and we're asked what is the speed up here at that point in time. So let's start by writing our kinetic energy equations. We have 2 objects that are moving in this situation. We have the gear that is translating and rotating, and we have the track that is just translating. So let's start with the track, which is the easy one. Translation is 1/2 mc, mass of the track, times the velocity of the track squared. Now the gear here is rotating and translating if we look at its center of mass. If we look at the instantaneous center, it is only translating. Or it's only rotating, right? Because the instantaneous center is not translating. The problem is here, so that would be 1 term, 2 terms if we're dealing with the center of mass. But we're given the moment of inertia around the center of mass. So we end up making more work for ourselves to get to 1 term because we have to translate this using the parallel axis theorem. So either way should work. We're going to use we're going to look at the center of mass. So if we're looking at the center of mass, we have a translation of the center of mass, which is 1/2 mass of the gear times the velocity of that center of mass squared. And we have a rotation of the center of mass, so 1/2 Ig omega squared. So we have 3 unknowns again. We need to use kinematics to relate them to each other. So if we look at relating omega to Vc and Vg. So let's do our relative velocity equations again. Vc is equal to, now I'm going to use the instantaneous center here, because that gets rid of a term. So Vc is going to equal the velocity of the instantaneous center, that's 0, plus omega crossed with r. Well, omega is in the k direction. We don't know what it is, but it's in the k direction, and it would be in this direction, right, based on the p, so that would be a negative k. crossed with R from the instantaneous center to C. So it's R of C as measured from the instantaneous center. So C is up here at the top. From the instantaneous center up to there is 0.3 in the positive I hat or J hat direction. So 0.3 positive J hat. So negative K hat crossed with positive J hat gives us a positive I hat equal to 0.3 omega I hat. We do the same thing with V of the center, G. We get VIC plus omega crossed with RGIC is equal to, all the directions are still the same, so we'd get 0.15 omega in the I hat direction. The directions now don't matter because these are magnitudes up here. So we get our final version here would be T. Plug in all the masses. We were given 50 for the center, the G. IG goes in down here. MC 25 goes in here. We'll plug in all the numbers, and we can write our T as a function of omega squared to be 2.078 omega squared. Alright, so second part is to look at the work. So if we look at the work 1 to 2, what is doing work in this case? So there's a force down here at the bottom, right, because the teeth are meshed. There's a force up there at the top because the teeth are meshed, but those are both internal forces. Well, the one on the bottom could be considered an external force, like a friction, but it acts at IC, so it's not going to do any work because IC isn't moving. Force P, we're going to look at a system that includes both the gear and the rack, right? So the force up here is our internal, so we don't have to worry about those. There's the weight of the gear and the weight of the rack, but both of those are perpendicular to our distance, so those don't do any work. So the only thing that's doing work is this P. So it would be P times the distance that P moves. So that distance is the distance the rack is moving. Now, how do we figure out how we're given information about the distance that G moves? How do we relate the distance that G moves to the distance that C moves? So once again, we have to look at the geometry and the kinematics of this. If we look at this as C moves, we're making a triangle, right? So as C moves this distance, G moves that distance. So by similar triangles, what we're saying is that, let's call this angle here theta. So looking at that similar triangle, we would have RG, let's see, shall we use sine of theta? No, tangent of theta. So tangent of theta is looking at the little triangle. The opposite would be the distance that G moves over the adjacent, which would be the RG, right? That same theta is in the big triangle, and so looking there, your opposite is DC, and your adjacent is RC. Well, we know RG and RC, so we can write DC is equal to DG times RC over RG, which is equal to 2DC. So if, 2CG, that's a G, sorry. This is also a G. Alright, so if DG moves 0.3, then DC is going to move 0.6. P is given as 150, so 150 times 0.6 is equal to 90. The work is 90. So now we can write our work energy. T1 plus U from 1 to 2 is equal to T2. It says it starts from rest, so T1 is 0. So we get 90 is equal to 2.078 times omega squared. Omega is equal to 6.5809. But we don't want omega in this problem. We want the velocity of the upper rack. We want VC. Well, VC right here is 0.3 times omega. So VC is equal to 1.97.